So now I want to talk about vertical dilation. So vertical dilation is when we multiply all y coordinates by a common factor, as opposed to horizontal dilation where we're multiplying all of our inputs, all of our x's by a common factor. So let's take a look at the same example we used in the horizontal dilation problem. So we have y equals x squared. And let's see what happens when we plug in 2 for x. So we have y equals 5. So we would expect if we were to graph out x squared plus 1 that the point 2, 5 would be on our graph. So now let's vertically dilate this function by 3. So to vertically dilate a function, what makes it different is we want to multiply all of our y values by some value. Let's vertically dilate by 3. So if we wanted to dilate by 3, since y equals all of this, we want to multiply all of this by 3. So we just take 3 and we put everything else in our function in parentheses to multiply. Alright, so let's see what happens with when we plug in 2 into this problem. Two squared is 4 plus 1. 4 plus 1 is 5, so 3 times 5 is 15. So we would expect the point 2, 15 to be on our vertically dilated graph. Now let's take a look at these graphs. So our original graph, our x squared plus 1 is in red, and our vertically dilated graph, y equals 3 times the quantity x squared plus 1 is our blue graph. And we can see our 2 points here, 2, 5, and 2, 15. So if you look at this graph, it kind of just looks like we took our red graph and we shifted it up 2 and then we squeezed it together. But if you're familiar with how transformations work, we didn't like do a shift, right? When you shift, you normally add 2 to something. Add 2 to just your function, and that shifts it upward. So how is this different? Well, if you notice, this point here is shifted up by 2, but this one's not shifted up 2, it's shifted up by 4. So it's not merely a shift. So maybe you think maybe we have to shift and then maybe do something with the horizontal dilation to make it squish together more. But there's actually a simpler way to look at it. So let's just observe some of the points on this graph. From here to here, our x-coordinate remains the same, but our y-coordinate went from 1 to 3. And the same thing here. Our x's are both 1, but we went from 2 to 6 here, and then 5 to 15 here. If you notice, for each of these, if you multiply each of these by 3, you'll get these 3 values here. And so that's actually what vertical dilation does. We can observe that all the points on our original graph have been all pulled away. They're being pulled away from the axis basically by the same multiple. So if you're observing a graph in the situation, don't always see this shift and just jump to, oh, I need to shift this first. Go ahead and keep that idea in mind. Well, first, check to see if the shift works for all points, and then maybe it's a shift, but it doesn't work immediately. Think of vertical dilation next. Think that possibly what's happening is each of the points is being pulled away from the axis by the same scale factor. So when I tutored vertical dilation, this concept wasn't so hard to understand. They understood basically if you needed to vertically dilate something by 3, that's real easy. Just put a 3 and put everything else in parentheses and multiply it. But what was actually harder to see is what I was just talking about, where you're observing a function and you're trying to figure out what you have to do to the function to sort of make it look like a different function. So let's go ahead and look at a problem that was posed in one of my sessions. So basically, this problem was something the student was trying to figure out. So our original function is the red function. So basically what we're trying to do is think of red as f of x. It's some function. In the problem, we're not told anything about the equation. And what we want to do is we want to change f of x so it looks like g of x, our green line. So how can we do that? So immediately it might be real easy to think like, oh, this, if we just move this up 6, this point gets to here. But then this isn't 6 points, so this isn't 6 units away from here. So maybe we have to do some sort of horizontal dilation to it. So, okay, so let's say we do go that route. Let's say we try to shift it first. And so our blue is just this function shifted upwards. So let's look at some points on our green line and our blue line here. Let's go ahead and hide some of the points we don't need right now. So we have this green line and we have this blue line, and what we're thinking is now that we've shifted this up to here, and now we're working with our blue line, maybe all we have to do to this blue line, I should be saying line, this blue function, is to maybe horizontally dilate it so it can stretch out to here. So let's see if that's true. Then what we would expect is there to be a common factor between these terms that would allow this to pull out to here. So that means that there's a common factor, like this goes from -2 to -6, this goes from 0 to -2, this goes from 2 to 0, and this goes from 2 No, that's not right. Let's look at these. So we'd expect there to be some common, let's just look at these 2 points, these 4 points. So we would expect there to be a common factor between -6, to go from -2 to -6, to 0 to -2. But there's no number we can multiply by, no single number that we can multiply these two by that would pull this to here and this to here. Like, we can multiply this by 3, and that would take -2 to -6, but if we multiply 0 by 3, we just get 0, so it doesn't pull out to this -2. So it doesn't seem like there's a way to horizontally dilate it after we shift it. So that's okay. Like, part of math isn't like immediately knowing, like seeing a problem immediately knowing how to solve it. So what we can do here is just like chuck that out. Okay, so it doesn't seem like shifting and horizontally dilating is working. Let's look at a vertical dilation. So let's go ahead and shut off these points. And yeah. And turn some of these back on. So what do we notice about I want this one, and I don't. That one, and 4, -6. Don't have that one. Put that up real quick. 4, -6. Okay, so what can we notice about these two things? Well, we notice if we go from -8 to -2, that's just multiplying by 1/4. So let's see if that works in other places. So if we multiply -6 by 1/4, do we get 1/5? If you can't do that in your head, let's just go ahead and try to go ahead and do it here. So 6 times by 1/4 equals 6/4, which equals 3/2, which in decimal notation is 1/5. So negative, 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 negative. So indeed, we've noticed that if we multiply the points, the y-coordinates in this on our original graph f of x by 1/4, then we get the y-coordinates in our other point, in our other graph, or g of x, by 1/4. So how can we write this? So say our red graph was just called f of x, And let's say our green graph was called g of x. And the question was, how do we manipulate f of x to equal g of x? Well, let's start with g of x. And what we noticed was sorry. And what we noticed in here is all we're doing is we're not shifting at all. We're just vertically dilating this graph by 1/4. And so that is real simple. So we just do what we did right here. We want to vertically dilate our graph by 1/4. So instead of using 3 here, we'll just do 1/4. We just put this all in parentheses, multiply it by 1/4. And if this were a question, then this would be your answer. So to get g of x from f of x, we just take our f of x and we multiply it by 1/4. We have vertically dilated our function by 1/4. And I hope that clarifies. So actually, the question one of my tutoring students asked me was, why can't we just move up and then look at a horizontal dilation? And I hope this kind of explains or gives you an idea about why it wouldn't work once we look at it, and then kind of hopefully gives you the idea that once shifting and horizontal dilation doesn't look like it's going to work, the next place perhaps you should go is just looking at a vertical dilation. I hope this helps.